In this video, we are going to understand the fundamental concepts of general relativity. We are going to stick to the basics. We are going to use simple mathematics, illustrations, charts and graphs so that the basic understanding is absolutely clear and we go and understand the roots. I would like to inform the viewers that this video is in continuation with my first video on the fundamental concepts. In case you have not watched, I have given the link in the I button. You can go ahead and watch it. But it doesn't matter whether you have watched the first video or not, because these are separate concepts and it has got no relation with the first part. However, I would request the viewers to go ahead and watch the first part of fundamental concept so that you can understand those concepts also and do not miss on that. My name is Shaunak and you're watching this video on my channel Physics for Students. I welcome you warmly. Before we go ahead and understand this particular fundamental concepts, we are going to just look forward what are the topics that we are covering. So we are just start with what we have left. We will also cover the manifolds and their need in general relativity. We're going to look into the differential geometry and why it is used in general theory of relativity. What is tensor calculus and what is the use in terms of GR? What is Riemannian geometry? What is called the Riemannian curvature tensor? What is parallel transport? And what is a covariant derivative? So before we start with this particular content, we will just like to have a quick recap on what we have done in the last video. So we started with the journey and we have shown how we migrated from special to general relativity. We also learned few important principles. Among them, the first was the principle of equivalence, where the gravity and acceleration and the free fall was being illustrated. What is the principle of general covariance, the laws of nature, and from that general covariance arises the need of tensors, because we need to get a tensor so that the movement along the graph and along the coordinates are covariant so that we can easily understand the changes. That led to Einsteinfieldequations and its components like Ricci scalar, Ricci tensor, stressenergymomentum and metric tensor. And we also learned what is geodesics and what is the movement that we do along the geodesics. Before we start, a quick correction that I would like to note from the last video. I made a horrible mistake, so my sincere apologies. In this particular equation of geodesic, this is actually wrong and this should be mentioned as this. So there will be alpha on the top followed by a delta and a beta instead of a alpha and a beta. This is the correct one, and in the second term this is wrong and it should be this one. So this is the right one, and this is being noted by one of my important subscriber, Bill Dance for you. So extended thank you very much, Bill, for keeping this as a note. So I have corrected it and I'm greatly thankful for pointing out this mistake. Okay, so let us start with where we have left. Now in general relativity we ended the video with what is called a geodesic. We get 2 points and a geodesic generalizes the notion of a straight line. So what is the shortest point that is required in order to travel from one point to another? In a flat space it is a space-time. So we get kind of a triangle like this and we get 2 points. Also we start from one point and join to another. In case that we get a curve, kind of a curvilinear coordinates and we use the same points, then it takes a curved line to join. So what this all those means is that further we get a kind of a curved surface and we get 2 points, we join. So importantly the world line, I would say, of a particle free from all external, I would say, non-gravitational forces is a particular type of a geodesic. So in other words, a freely moving or falling particle always moves along a geodesic. I will try to illustrate with the famous example of Amol Kumar Chaudhary. In an interview he told that what if a tram line is given on a certain road and you ask a mathematician that what would be the way in which the tram will follow. So the mathematician will tell that you give me the initial conditions, and if it is a second order partial derivative, then I can use f equal to ma with two variables and I can immediately calculate it. But if you ask a rickshaw puller that what is the way in which the tram is going to travel, he would say this: it is just going to travel in the path which is laid out. That is particularly geodesic. A classical and a wonderful example, so simple, illustrated by Professor Amal Kumar Chaudhary, one of the important contributors from India on generalrelativity and singularity principle. So what is the essence is that geodesic is basically the laid out tramline which generally moves, and it is the shortest possible path. So here it is, the geodesics are simply the shortest path between the points. So if you continue with this, what we get is that the straight line is basically a generalization. So it is a notion of straight line to curved space-time, and the gravity, as we know, is due to the curved space-time. And what is responsible for causing the gravity is the stressenergymomentumtensor. So we can conclude that an object moves through space-time in a straight line, which is called geodesic. But if the space-time is curved, that means if gravity is present, this line will follow the curvature and may change the direction. Note that I don't want to say that space-time, when it is curved, only its gravity is present. In context with GR, space-time curvature denotes gravity, and it may change the direction. So like if you are moving on a surface of a sphere, for example, then things will move in a different way. So we actually, and this effect is generally, which is called a gravity. So I would like to tell what I wanted to show you here is that the path of a planet orbiting a star is the projection of a geodesic of the curved four-dimensional space-time geometry and of the star onto a three-dimensional space. So that is where actually we ended the last video, part 1. So just to give you a quick wrap. So here is a sphere, and these people are moving around this. So at some point of time, you tend to meet. This is the sphere also. These are the geodesics. So these are the lines which are joining the points, and this is actually called the great circle. So this denotes again the shortest path between 2 points in a surface, and geodesics are the trajectories of the moving bodies under the influence of gravity, which causes the curvature, and in that curvature the particle moves. Okay, so that is what I wanted to give you a quick recap, and now let us get into the main point of this video. So first we will start with what is called a manifold in general relativity, and why do we need a manifold. Okay, so first of all, its use allows generalization from classical Euclidean space. So let us see. So if we got 2 points and we are joining these 2 points in Rn, and if we get a kind of a curved surface and we get the same points, then what we get is a kind of a curved line, right? So on a sphere, if we get these 2 points, then it is again going to get a kind of a curved line. So what we are going to do is that we are going to differentiate this manifold, this one as well as this one. Why we want to differentiate? Because until we differentiate this, we won't be able to apply calculus. Why do we need to apply calculus? We need to apply calculus so that we can do calculation. Simple. So if you draw a triangle typically on a curved sphere, the angles won't be equal to 180 degree compared to that of a flat Euclidean space, then the angle is equal to 180 degree. So we differentiate the structure in order to get a better understanding using calculus. So this is the need of a manifold from classical Euclidean spaces, and as general relativity by construction distorts space and time, manifold is a proper word to describe the coordinates as distorted from the Euclidean space. So a manifold offers the most general setting, I would say, that we can use in calculus, right? So this is something we start with the need of a manifold. Okay, so now what we get is that why do we need a manifold, right? So let us understand in this way that from Euclidean we are moving now into non-Euclidean, right? From flat space we are also moving into a curved space, right? From inertial frame of reference we are moving into non-inertial frame of reference, because general theory of relativity is all about non-inertial frame. And from space and time, which was separate in Newtonian mechanics, now we have assembled into curved space-time. And all this will lead to a surface. We need a surface to do the calculation, which is called a manifold, and we need it should be differentiable so that we can apply the rules of calculus. So this is the beautiful thing, that is that a differentiable manifold gives tools to do that. So the way you create a measure of distance which allows you to calculate shortest paths between points, even if you don't have an ambient space. So just to tell you that from Euclidean, once we move into non-Euclidean, that is curved space. From flat we are moving to curve, inertial to non-inertial. All these changes are happening because we need to calculate, because GR is all about curvature, and we need a surface, and that should be differentiable so that we can apply the rules of calculus. So this is an important thing. I think the need of manifold in GR is quite clear. Now if you get a kind of a curved surface like this, and this, all those curvatures which we get, a hyperboloid, sphere, or whatever, I mean to say, I've just drawn some crazy bit of curves. Now all this would be locally Euclidean. That means they are locally isomorphic to Cartesian space in Rn. Now I will just explain you what do I mean by locally Euclidean, because the fact is that until we get a locally Euclidean space, we won't be able to do the calculation. So we need to, the manifold is basically where this becomes locally Euclidean, and it is somehow related to Cartesian space or Euclidean space. Okay, so we get a kind of a surface like this, and we call it as a manifold. Further we call it as a differentiable manifold. Why? And a differential manifold because we can use calculus, and this differential manifold should be locally Euclidean. So why we need to have it locally Euclidean? So that we can use differential geometry, so that this space-time, which is a 4-dimensional x, y, z and t, can be lumped up into kinds of a space-time manifold, right? So we get a surface, we call it a manifold. We call it a differential manifold so that we can use differential calculus, and this differential manifold has to be locally Euclidean, otherwise we won't be able to do the calculation. And we do those calculations using differential geometry, and the space-time is now into a space-time manifold, because otherwise we won't be able to calculate. So this is a kind of illustration which I would like to show you. This is a point, right? And we further zoom it here, and then if we further zoom it, we get something like a simple point on a Cartesian space. So this is something which is locally Euclidean. Very, very important. Just wanted to show you that how a particular point which is in a curved space-time, you zoom it and zoom it and zoom it further, it gets to a simple point where we can apply the Euclidean rules, the rules of the games, differential geometry, everything. So that is why we need a manifold, so that we can use those simple calculations on a space-time which is curved and which should look locally Euclidean. Okay. So here comes a simple definition of a manifold. Some manifolds are topological space which deals with numerous shapes and forms which are bent, furled and wrapped. So if you take a visual understanding, this becomes clear. So every point you can see there's a Klein bottle, a hyperboloid and different types of shapes. So every point on those surfaces that you can see has a small area which looks like Euclidean. Just show you another example. So if we visualize this sphere, and there's a person who is standing over here, and this person starts to move from here to here, and then to here, and further to here, and then to here. He keeps on moving and moving and moving and moving. Now we get a kind of a surface like this. So what we are doing is that we are magnifying that sphere, or we are extending this sphere into curved space. Here also the same person starts moving from this point to this point, to this point, further to this point, and to this point. So what is happening, you see, there's this actually locally resembles of a Euclidean space near each point. Because on the right hand side, if you see that the person who is moving along, for him it is absolutely flat. Because we see on a extrinsic curvature, so it seems that it is a sphere and people are moving in different directions, but it is not so. For that person staying on the curved space, which is there, you can just simple a creature moving around, that locally resembles Euclidean, and that is basically the beauty of a manifold. So something which is projected and becomes a kind of a locally Euclidean space. So on the left hand side, this sphere is a global one and this is a local one. Each point on this we can use calculus or whatever the rules of mathematics. Okay, so we can use the manifold definition. A manifold is a topological space that is locally Euclidean. So we get a kind of a sphere and we point this one as a neighborhood which uses the tuples like x1, x2 and goes up to xn. This is Euclidean and Cartesian space is a space of all real numbers, and a locally Euclidean space is a topological space that looks like Rn. This is most important. So this is, I mean to say, this is an extended definition of manifold because this is important in order to understand. So the points in the neighborhood can be used by this, and Euclidean Cartesian space is a space of all real numbers. So this one is local and this one is Euclidean. Now, if we analyze the manifold, I mean to say the surface, you will see that on a sphere, when we move along, I have just shown that two persons are meeting at North Pole. The same this is called a positive curvature. This is important because once we start moving along the geodesics, this will be important. But this kind of a cylinder shape, this is something which is called a zero curvature because all of them are parallel. Now, this one is, diverging, or they are spreading across. So this is something which is called a negative curvature, right? So if you get a kind of a surface like this, what we start doing is that we want to break and break and break and break into finer pieces until we perform calculus, that is dy and dx, and this is the differential area, and we are applying the rules of calculus on the manifold. So you see how it happens that this dA, or the this graph, is now being differentiated, and we can use calculus on that, and that is why the manifold now takes the shape, and we can use now the calculus rule to calculate where it is going from which point to another, positive, zero, or negative curvature. So as you see these yellow boxes, if we further zoom into that, this looks like a locally ordinary Euclidean space. That is why we need a manifold. So we can also tell that these yellow pieces, these actually extends up to something which we call Rn. That is a real number up to n, and this is something which is isomorphic to the Cartesian space Rn, which we told you right at the beginning of this video, that a manifold is a space. Now you see all these hyperboloids and sphere, once we break it and use calculus, this becomes isomorphic to Cartesian space, which is in the real number, right? Okay, so just a quick understanding on a very interesting part, that who actually discovered this. So Bernhard Riemann, this person, I think we are all aware, was the first to do extensive work generalizing the idea of surface to higher dimensions. So the name manifold actually comes from this word, which I won't pronounce with my horrible German pronunciation, which actually William Kingdom Clifford translated as manifoldness. So that is how the word comes. Now this in his Göttingen lecture, inaugural lecture, Riemann described the set of all possible values of a variable with certain constraints as this one, the discrete continuous manifold. Now he distinguishes between the continuous manifoldness and discontinuous manifoldness depending on whether the value changes continuously or not. Now, as continuous example in this lecture, Riemann refers not only to colors and the locations of objects in space, but also the possible shapes of spatial figure. Using induction, Riemann constructs something which is called the n times extended manifold, or n-dimensional manifoldness, as a continuous stack dimensional manifoldness. Riemann's intuitive notion evolved into today what is called a formalized manifold. So this was just a kind of an idea on the opening Göttingen lectures which he gave in 1854, and that actually changed the entire course of our understanding of history, and it actually is considered as one of the most revolutionary paper ever produced by Bernhard Riemann. So what do we understand from this? The fundamental concept number one coming up first in this video, that manifold offers a general setting where we can use calculus. This is important, and the basic physical constructs representing gravitation, a curved space-time, is modeled by a four-dimensional smoothly connected Lorentzian manifold. Now, If you don't understand the word smoothly connected, don't worry, I'm not going to expand on that. However, I have got a lecture on what is called a smooth manifold on the basic concepts of differential geometry. You can go and check out in the playlist of differential geometry. We get a very extended and comprehensive video on what is called smooth manifold. So take number 1. Manifold is a general setting where we can use calculus, and the basic physical structure representing gravitation needs to be modeled in a smooth connected Lorentzian smooth manifold. Right. So now as we see that Riemann has almost changed the entire understanding of geometry, and this is the time when the advent differential geometry actually started taking shape. So that is why we call the advent of differential geometry in general relativity. Now if you see all this type of curves and graphs which are coming rotating, you can see a parallel transport right on the right hand side, a saddle shape, and all those graphs. Then in order to calculate and make calculations further, we know that necessity is the mother of invention. So with Bernhard Riemann, setting the set of differential geometry ablaze with fire. So the need was the invention of a different kind of a geometry for the measurement of different types of curvature. All these tensors, parallel transport, Riemannian manifolds, covariant derivative, tensor formation, Riemann curvature, and geodesics led to the formation of differential geometry. Why I am talking on those aspects is because along with our understanding of fundamental concept, it is important for us to understand how the things evolved through the passage of time in the annals of history, right? So these things which you're seeing right at the bottom, parallel transport, Riemann manifolds, this eventually led to what is called a differential geometry. Right. So the birth of non-Euclidean geometry first started with this gentleman. Nikolai Ivanovich Lobachevsky was a Russian mathematician, founder of non-Euclidean geometry, and which developed independently of Janus Bollai and Carl Gauss. Now Lobachevsky is called the Copernicus of geometry for his profound influence and development of non-Euclidean thought. Now Lobachevsky actually grew up at a family of moderate means. Family relations, well, however, were evidently strained. After 1791, his mother was effectively divorced from her husband, Ivan Lobachevsky. Now Lobachevsky teachers were German professors, right? Invited to the university, in particular the mathematician Martin Bartels, and a friend of Carl Gauss, noted for his encyclopedic knowledge of mathematics. In 1812, Lobachevsky received a master's degree from the university, and in 1814 he received the degree of adjunct of pure mathematics and a permission to teach independently. In February 1826, Lobachevsky presented the Physico-Mathematical College the manuscript of the essay devoted the rigorous analysis of theorems and parallels, in which he may have proposed a proof of Euclid's fifth postulate. Now, in his geometry, Lobachevsky abandoned the parallel postulate of Euclid. Instead, he based his geometry on an assumption: in the plane formed by a line and a point not on the line, it is possible to draw infinitely many lines through the point that are parallel to the original line. It was later proved that his geometry was self-consistent, and as a result, that the parallel postulate is independent of Euclid's other axioms and hence not derivable as a theorem from them. And this is where the entire trigger of differential geometry was set off. So from taking off from Lobachevsky, there was a huge change in the mathematical arena. The subject of differential geometry emerged in the early 1900s in response to the foundations of contributions of many mathematicians, including R.A. Poincaré, one of the foundations of topology. The notion of topological space later was a little bit distilled by Felix Hausdorff in 1914, and in 1942 there were many different notions of manifold of a combinatorial and differential geometric nature. It was Elie Cartan who helped to formulate the formulations of differential geometry of smooth manifolds in terms of exterior calculus and the theory of moving frames, leading to the world of physics to Einstein-Cartan theory. Following the early development of many mathematicians who are contributing, including Jean-Louis Cauzoul, who introduced the connection on vector bundles. Following that, there has been a lot of change, including 1930, Sir William Hodge, who used the Hodge theory, and I would like to tell you very recently, 2022, June Hu actually used Hodge theory, and he earned his Fields Medal in 2022. Fiber bundle was introduced by Riemann in Riemanns contraction, and most importantly, Sir Michael Francis Atiyah, who doesn't know this great person. He actually won the Fields Medal, Abel Prize, and he made huge amount of contribution in the field of mathematics, and even tried to prove the Riemannian hypothesis. Sir Atiyah collaborated with many mathematicians. His three main collaborators, as you see in the screen, was with Raoul Baut on the Atiyah-Baut fixed point theorem and many other topics, Isidore and Singer on the Atiyah-Singer index theorem, and with Friedrich Hirzebruch on topological K-theory, all of whom he met at the Institute for Advanced Study in Princeton. Well, this is more or less a kind of a quick, I would say, history or journey through the areas of differential geometry. Okay, so we now come to the fundamental concept number 2. So we know that differential geometry, as you see, was developed independently as a subject of study. Later it was integrated by Einstein, and as general relativity denotes gravity in terms of curvature, the underlying mathematics, all of them lies in differential geometry. So this is point number 2 of the fundamental concepts in this video. Okay, so where do we start? We get into the next part, which is called development of tensor calculus. We have seen why tensor is being used for the invariant nature in the first video, and here we are going to look at its application in general relativity. So it was first started in 1822. As a quick recall on the tensor calculus by Cauchy, introduced the Cauchy tensor in continuum mechanics. The Cauchy stress tensor is used for stress analysis. It was then followed by Sir William Rowan Hamilton, and in 1846, he's an astronomer and a physicist, and he made major contributions to optic classical mechanics as the first person to coin the word tensor. It was in so the tensor of the quaternion is being first found by William Rowan Hamilton. If you really want to know the development of tensor in general relativity, there is a separate video of mine where I've spoken only about tensors and their usage in general relativity. Then comes this great person, Bernhard Riemann, who introduced the Riemann curvature tensor, followed by Joshua Willard Gibbs, introduced tensor products, as in R3, which was then called indeterminate product and applied to study. He later extended the indeterminate product to n dimensions in 1886. Further, we find another gentleman, William Voldemar Voigt, who used tensors to describe stress and strain on crystalline structure in 1898, and the term tensor first appeared in the modern physical meaning. We come across another very popular person, Gregorio Riccicurvatureexplained, used in the late 1800s, and in introducing Ricci tensor, and then Tullio Levi-Civita, who introduces the tensor calculus, quite well known. And this is a basic idea on how the development of tensor calculus is being done. Now, tensor calculus is not complete until we mention one name, that is Marcel Grossmann. This person was born on the 9th of April in 1878 in Budapest, Hungary. He is a Greek mathematician. He is a son of a large machine shop owner. He was the descendant of an old Swiss family originating from Hong near Zurich. He spent his childhood and attended primary school in Budapest. After graduation, he started at Swiss Polytechnic School in Zurich, which is called ETH, in the School of Mathematics from 1896 to 1900, and here he met with Albert Einstein and Mileva Maric, the only woman in that class. So they studied together calculus, analytic geometry, descriptive geometry, and whatnot. It was Grossmann who helped Einstein with the geometry of the concept of tensor algebra. He needed to formalize the theory. He asked Grossmann to search the literature and look for existing appropriate geometry to tackle such questions. and Grossman happily did that. So it is important to note that it was basically Grossman who first introduced, and we will see the evidences of his papers, how he introduced to young Einstein. So this is the top portion of the Zurich notebook. This notebook documents the scratch for a generalized theory of relativity and the theory of gravitation during the period of collaboration between Grossman and Einstein. And this page shows that Grossman introduced Einstein to the Riemann tensor as a mathematical resource for his general relativity. So you can see, we will just, if we magnify this paper, so let us do that, and what we find is this part, right? Grossman had shown Einstein the relevant object that would open up path fully covariant general field gravitational field equations. So next to the definition of the crystal symbol of the first kind, which is right there, and we find on that page this one, which is a Riemann Christoffel tensor in full covariant form. This one, the right at the bottom. And next to this article, if you see this one, which I have marked in red, this is basically what is called the Grossman tensor of fourth manifold. Since such an object was needed only because of two free indices, Grossman contracted the Riemann tensor once. Clear evidence showing the help of Marcel Grossman, how he introduced the differential geometry and part of Riemann curvature tensor and the tensor calculus to Einstein. Now, so what we see is that this kind of curved surfaces and this type of surfaces require the study of curved surfaces. And why we need? Because we need to have a kind of a differential manifold. This is just a sequence which will make things further clear. This differential manifold is required because we need to model it in a space-time manifold. This space-time manifold follows certain rule of tensors, and tensors are invariant under the change of coordinates, and which leads to a system where the laws of general covariance, which is a basic postulate of general relativity, is being followed. So what we get in here is a kind of a complete picture of development of tensor calculus across and how things happened from a curved space-time to differential manifold to tensor, which leads to invariance of the system and forming a general covariance laws of physics. Okay, so what we come is the third fundamental concept in our video. Tensor calculus was definitely developed as an independent subject of study, and in general relativity we use tensors to study the transformational behavior and other changes to formulate coordinate independent laws, because we need to have a fully covariant system where the coordinate independent laws will help us to calculate. Right, so we come to the next part of our video, which is very important. It is called Riemannian geometry and Riemann curvature tensor. So it is difficult to formulate Riemannian curvature tensor, but before that we'll have a quick understanding of what is a Riemannian geometry. Now, Riemannian geometry is also called elliptic geometry, one of the non-Euclidean geometries that completely rejects the validity of Euclid's fifth postulate and modifies his second postulate. Now, Riemannian geometry is definitely a branch of differential geometry that studies Riemannian manifolds, smooth manifolds with the Riemannian metric. So, general relativity is a theory of gravity. We know that gravity is a curvature of space-time. Hence, we need to study the curvature which generates space-time and manifolds using differential geometry. Riemannian geometry is a branch of differential geometry. It is very broad and abstract, and it studies Riemannian manifold, smooth manifold, and is Riemannian metric. So it is just a kind of a very gross and a basic definition of what is a Riemannian geometry. Now, the Riemannian geometry, if we talk it in technical terms, in mathematical terms, it would be a type of non-Euclidean geometry developed by Bernard Riemann. There is a Riemannian space n-dimensional, so we are extended to m dimension, to a differential manifold M of super n with n coordinates x1, x2 and xn, and we get the distance through this kind of a quadratic formula, ds square equal to sigma, which you can read, and this is basically tensorial form. I have explained more about this particular form in my video metric tensor, and you can watch it in my playlist of general relativity. Okay, so just to go ahead, that this is basically the the book which which actually was written by Riemann on his inaugural lecture at Göttingen, which I have just seen, and it was the famous mathematician William Kingdon Clifford who translated it. So this is something very, very fundamental to general relativity, which was studied by Grossman and others. As we have seen, it is an independent field of study. Then it was used and incorporated by Einstein, which Marcel Grossman, Michel Besso made important contributions, and Riemannian manifolds, smooth manifolds, is being used by Einstein to formulate a kind of a comprehensive theory. So what is the fourth concept coming on our way for this video? So Riemannian geometry is basically an independent branch, and it is much more a generalized form of differential geometry, and it enabled the formulation of Einstein's general theory of relativity because it spurred the development of algebraic and differential topology, which we are not going to discuss out of the scope of this video. So it is a generalized form of differential geometry, and because of its nature of study, it helped Einstein to formulate the theory of relativity. Okay, so what we found now come to the most important part, which is called Riemann curvature tensor. Now, if I go for a kind of a simple definition in the mathematical field of differential geometry, the Riemann curvature tensor, it is also called Riemann Christoffel symbol, is the most common way used to express the curvature of a Riemannian manifold. Riemannian curvature tensor is a tool to describe the curvature of n-dimensional spaces such as Riemannian manifolds in the field of differential geometry. It assigns a tensor. Now, ordinary partial derivatives commute, but covariant derivatives do not. We're going to look into it a little bit. Riemann curvature tensor is defined as a measure of their failure to commute. So this is, I would say, a kind of a basic definition of Riemann curvature tensor. However, things will be much more clearer once we look into this. This is a kind of, I would say, mathematical part of Riemann curvature tensor. It includes parallel transport. We are going to look covariant derivative. We are going to look Christoffel symbol, not right now. So Riemann curvature tensor gives a complete description of any curved space. It is Ricci tensor actually is a contraction of Riemann tensor. Now, if you look into this, this is the Einstein field equation. I have covered this, I think, into 2-3 videos comprehensively. But you might wonder that where is the Riemann curvature tensor, right? Because if you expand those, it is not found anywhere, but it is there lurking in this particular field equation. This is the riccicurvature tensor, which we can see as R sub mu nu. And this is also the Riemann curvature tensor because it is in contractual form. Let us see how. So the Riemann curvature tensor is this one, where this is the Ricci tensor and this is the Riemann curvature tensor, right? So Ricci curvature tensor is the contraction of the first and the third index. So here is the tensor, and this is the first one, and this is the third one, and both of them have been contracted. That means each component of the Ricci tensor is the sum of multiple components, and it leads to this. So you see that actually this Ricci tensor has been contracted from the first and third indices of Riemann curvature tensor, and that is the first element of Einstein's field equations. Okay, so now we got an understanding of Riemann curvature tensor, but how to visualize, right? How to see it in geometry. So we use this concept which is called parallel transport. Parallel transport actually provides a way to compare vector in one tangent plane to a vector in another by moving the vector along the curve without changing it. Let's see how. So if you want to compare these two vectors, we know this one is bigger and this one is smaller. Or we can slide that vector into another and we can just compare, right? But it is a way of comparing vectors at different positions in the manifold. It is a way of transporting data also through a surface in manifold. Now, if we get a kind of a flat surface like this, which is a kind of a triangle, so make a point, right? And we put it an arrow. This is the yellow vector, and we are going to parallelly transport it. Why? I will soon tell you. So we move along this one. Remember that we have to preserve the length, so we cannot move any other way. And we further move, and we further move. Then keeping things in parallel, we move further over here. 1, 2, 3. I've just skipped these steps. Then we go into here, and we get into here. And finally, you see this black one. which is overlapping with the yellow one, it shows that if we parallelly transport a vector along this closed curve or a closed surface in a flat space, it comes back to the original point. That means there is no curvature. So in a flat space, when we parallelly transport a vector, it actually comes back to the original place. So this is what we call parallel transport, but in a flat space. But it is always not that. So let us imagine this is a sphere and we are standing on the top of the sphere and we want to get to this blue point and we are carrying an arrow in our hand and we want to keep it as straight as possible. So we move here. So V is the vector. So we move here. We are trying to keep it. We are trying to keep it as simple, as straight as possible. But you see, due to this curvature, the vector is bending. So if you move around this great circle, we take it here and we take it here and we take it. So the vector points somewhere else. So the direction of the vector changes due to the curvature, which is in black on the right hand side. Now, if we want to go around this way, I would like to show you again this green way. So we are again trying to keep it as straight as possible. We are going here, and this blue vector is the ending vector. So clearly you see, compared to the flat space or the Euclidean space, in spherical coordinates or in a curved space, the vector is not the same. So we call it as V prime. Now we take out those two vectors, right? And then we try to measure. We get a kind of a formidable distance, a space or a gap which has formed. So V and V prime. And this is denoted by the Riemann curvature tensor. So the Riemann curvature tensor essentially, in a very simple language, describes the change of all the components of this vector in space-time direction. Now, you see that if we now talk about the basis of vectors which changes, if you have seen my earlier video where in curved space we see that the basis of the vectors changes, that is how the Riemann curvature tensor evolves. Now, if I take the equation again, this part which I marked in red is actually what points to this. So, what we can tell is the Riemann curvature tensor gives a complete description of the tidal forces of general relativity, which we will deal with this, but this is also important. What is important in Riemann curvature tensor is that when we are trying to parallelly transport the vector, the difference that it makes, it describes the change of the component of this vector. Right. So when we parallelly transport the vector, we see that we are trying to keep the vector constant as much it is possible, but unfortunately we are unable to do that. So the parallel transport cannot keep vectors constant, and here we introduce a new concept which is called a covariant derivative. Just note that it is a derivative. Ordinary derivatives are they commute, but in a curved space they do not, and you're using the term covariant because at the end of the day we want to find out something which covaries. So this is something which is denoted by this nabla sign. This one denotes the direction and this is the vector field. So actually it denotes the rate of change of a vector field. That means covariant derivative is a tool which helps us to find parallelly transported vector fields. We try to make it as simple as possible, but we're unable to do that. So we use the covariant tool which helps us to find parallel transported vector fields. Okay, so what we can now see is a few important points. Parallel transports cannot keep vectors constant. We have seen that. It is impossible to find the constant vector field on a curved surface. Parallel transport keeps vectors constant as we move one by one, taking baby steps. In flat space, covariant derivatives are just ordinary derivatives, and covariant derivative helps us to find the parallel transported vector fields. Covariant derivative is a generalization. If you know directional derivative, it's just generalizing the directional derivative. So you see here, this is something in flat space. So it is just the ordinary derivative del u by del ui. It goes up to I. And in case we get the covariant derivative equals to 0, that means that the vector v is successfully parallelly transported in the direction w. In the direction it should be u. Anyway, it doesn't matter. So what I am trying to tell is that the parallel transport, which is trying to keep the vector constant, yet it is impossible. And the covariant derivative is a tool which is trying to get the parallelly transported fields. And in case we find the covariant derivative to be 0, means that the vector has been parallelly transported. So derivatives actually works differently in curved space. Now, in curved coordinate system, apart from the components of the vectors changing, because they are functions of the coordinate themselves change. So in curved coordinates, apart from the components, the coordinate also changes. So covariant derivative, which is the generalization of an ordinary derivative, works actually in any coordinate system. A covariant derivative fixes that since it takes into account all the necessary changes, and it is acting as a correction terms. So this is a kind of a equation where this is actually the ordinary derivative. This is actually the extra term which is used for the coordinate change. Mind it, this gamma term is the Christoffel symbol, which we will not cover in this video. You can see how this indices changes from one point to another. So this is a kind of a nice understanding what actually covariant derivative does. And it is basically a generalization, and it fixes that since parallel transported things cannot go. So you can just go back to the earlier part where I would like to show. Yeah, so this is the one. So you see in this one that covariant derivative is actually a tool which helps to find parallel, because we can see that it is impossible to keep the vectors constant, and in flat space it is equal, and it is 0 in case it is parallelly transported. So now this is something very important, because we need to understand covariant derivative, without which understanding of parallel transport won't be clear. So here is the final part. So in general relativity, it is a covariant version of the ordinary derivative, and in general ordinary partial derivatives are not covariant in nature. Our target is to find the covariant physical law. Just a few important points. Covariant derivatives should replace ordinary derivatives when we are dealing with curved spacetime. If we do not, calculations are wrong. So to obtain a general covariant law of physics, which is a basic postulate of GR, we need to replace all the ordinary derivatives with covariant derivatives. And in general relativity, we are dealing with curved spacetime. The ordinary derivative is not useful. So what is the fundamental concept number 4 coming up in this video? The Riemann curvature tensor, which we have just learned, describes the change of all the components. So you can just visualize those two vectors we are taking out, and we are trying to measure the gap of a vector as it moves along the space-time curvature. It is local invariant of Riemannian metrics. That means on the metric which we will see later, it is invariant, obviously, otherwise we won't be able to calculate. And it measures the failure of the covariant derivatives to commute. We have just seen that. Fundamental concept number 5 is that covariant derivatives helps us to find parallel transported vector fields. That is the tool which we are using, right? And we can use this tool into metric tensor and any other further metrics. And covariant derivative, which is the generalization of an ordinary derivative, is working in any coordinate system. This is the fundamental concept number 5. So, okay, what is the summary that we have learned in today's video? We have learned what is the usage of manifolds in general relativity. We have also understood manifolds. We have seen an interesting history. Differential geometry, how it is independently developed and then used in general relativity. Development of tensor calculus. What is a Riemannian geometry? What is Riemann curvature tensor? How it happens in parallel transport, and how covariant derivative is a tool for understanding those which are parallelly transported vectors. Right, so in the next video, we are going to look a little bit more into covariant derivative, and most importantly, the Christoffel symbols. We're also going to look into the curvature of general relativity, how it leads to black holes, singularity, and time travel. That's all in today's video. I think you have enjoyed. I am continuing with this in the third part, comprising of these important topics, and more or less after that, our fundamental concept will be done. Do let me know how did you like the video. Anything that you would like to share, please share it in the comment box. Please like, subscribe, and click on the bell icon to get all the notifications from Physics for Students. This is Shaunak signing out from Physics for Students, and wish you a great day and a great weekend ahead. Stay safe and stay happy. Bye.